right, so I will be going through problem 2 of the 4 problems in part B as one of my problems that I'm presenting. So this problem is set up as x double prime plus 3x equals h of t, where h of t is this function that is 0 whenever t is less than 5, and it is 2 sine of t minus 5 whenever t is greater than or equal to 5. And we're also given these initial conditions for the function x. And our job here is to solve for what the original function x would have been based upon this differential equation. And so when I see this format for the h of t function, I know we'll have to rewrite this as a unit step function in order to use Laplace to solve this. So that's the first thing I did. I rewrote it as x double prime plus 3x is equal to unit step function starting at 5 times 2 of times sine of t minus 5. We don't have to worry about the 0 part because the unit step function just assumes that it's 0 whenever it's has not gotten to the t equals 5 point yet. So that's how we rewrite it as that, and then the next step will be taking Laplace transform of everything. So that looks like this: L times x double prime plus 3 times L of x is equal to the Laplace transform of all of this stuff over here. And we'll break that down a little bit more here in the next step. So Laplace of x double prime, based upon the equation from class, will become s squared times L of x minus s times x of 0, which in our case x of 0 is 1, and then minus x prime of 0, which was 0 in our case. And then this 3 L of x comes along, and now for the Laplace transform of a unit step function, what we have to do is it becomes, the unit step function starts at 5, so this becomes e to the negative 5s, and then we have to multiply by the Laplace transform of whatever function was beside the unit step function, but we have to plug in a t plus 5 into that function. So this becomes e to the negative 5s times Laplace transform of 2 sine of t plus 5 minus 5. And as you can see, this plus 5 and minus 5 will cancel, and this will be just the Laplace transform of 2 sine of t, which is pretty simple. So we'll simplify this a little bit. We'll pull the Lx terms together, and that'll become s squared plus 3 times L of x, and then minus s. And then on the right side here, like I said, this is just Laplace transform of 2 sine of t. So then that will simplify to 2 times 1 over s squared plus 1. And then the e to the negative 5s is there as well. So we will carry this over to the next page. And the next step is going to be solving for this L of x term. That's what we want to try and do, get this isolated on the left side alone. So we'll add the s over to the right side, and then we'll divide by s squared plus 3, divide the entire thing by s squared plus 3. So now we have L of x isolated, and on the right side we have e to the negative 5s times 2 over s squared plus 1 times s squared plus 3 plus s over s squared plus 3. So I'll carry this equation to the next slide where we have a little bit more work to do before we convert back to the original language. So this right here, s squared plus 1 times s squared plus 3, is not in any really good format to, it's not in any of the formats that are on our table to convert back to the original language. And so we'll have to use a partial fraction decomposition calculator to separate these things. And that comes out to being these two terms here, 1 over s squared plus 1, and then minus 1 over s squared plus 3. And then I just distributed the e to the negative 5s term into both of those things just to make sure I remembered that it was being multiplied by both of these functions. And then this term here, s over s squared plus 3, just comes along for the ride. That is in a good format to be translated back to the original language already. And so this next step gets a little bit interesting, but it's not too bad. So if I ignore the e to the negative 5s, and I just look at this 1 over s squared plus 1 and this 1 over s squared plus 3, those are pretty simple to convert to take the inverse Laplace of and go back to the original language. This would just be sine of t because it's a over s squared plus a squared. And this one here would be a little more difficult, but it would just be 1 over square root of 3 times sine of square root of 3. A over s squared plus a squared is the format for sine. So this would be, our a here would be square root of 3. And so we would need a square root of 3 on the top. And in order to account for that, when we take the inverse Laplace, we make it 1 over the square root of 3. So if we ignore the e to the negative 5s terms, that is what these would, the inverse Laplace of these would be. But we can't ignore those terms. So we'll go to the next page here. And basically what we have to do is these e to the negative 5s terms tell us that it's going to be unit step function starting at 5. And then we have to take this, what this function would have inverse Laplace back into, which was sine of t, and just plug in the t minus 5, because it starts, the unit step function is starting at 5. And then when we also look at this other one over here, it's the same thing, unit step function starting at 5. And then we have to plug in the t minus 5 to what this thing would have inverse Laplace back into, which was the 1 over square root of 3 times sine of square root of 3t, but now it's square root of 3 times t minus 5. And then this last term over here, s over s squared plus 3 becomes cosine of square root of 3t, because the format for cosine is s over s squared plus a squared. So our a there would have just been square root of 3. So this is our final answer then. This is the x of t function that solves the initial differential equation.